Welcome! In this session, we'll tackle an interesting problem titled Count Equal and Divisible Pairs in an Array. We'll explore the challenge, break down the solution, and understand the key concepts involved. Let's dive in. In this problem, we are working with a zero-indexed integer array called nums, which has a length of n and an integer k. The task is to find pairs of indices, I, j, that meet three specific conditions. First, the indices must satisfy 0 equals I less than j less than n, meaning I has to be smaller than j. Second, the elements at these indices, nums, I, and nums, j, must be equal. Finally, the product of the indices I asterisk j must be divisible by k. Once we identify all such pairs in the array, we need to return the total count of these valid pairs. The input constraints ensure that nums can have between 1 and 100 elements, and both the elements of nums and the value of k are guaranteed to be integers between 1 and 100. The output will be a single integer representing the total number of valid pairs. Let's consider an example to understand how to identify valid pairs. Suppose the input array is nums equals 3, 1, 2, 2, 2, 1, 3, and k is 2. Here, we need to count all pairs I, j, where nums, I, is equal to nums, j, and I asterisk j, %2 equals 0. For instance, the pair 0, 6 is valid because nums, 0, and nums, 6, are both 3, and the product of their indices 0 asterisk 6 is divisible by 2. Similarly, the pair 2, 3 is valid because nums, 2, and nums, 3, are both 2, and 2 by 3, %2 equals 0. Other valid pairs include 2, 4, and 3, 4, each satisfying both conditions. When we count all these pairs, we find there are 4 in total. This is why the output for this example is 4. Now let's look at another example where the input is nums equals 1, 2, 3, 4, and k equals 1. Here, we need to check for pairs I, j, where nums, I, is equal to nums, j. However, in this case, all elements in nums are distinct, so there are no pairs where nums, I, equals nums, j. As a result, the output is 0. In contrast, if we consider an array where all the elements are the same, such as nums equals 1, 1, 1, 1, and k equals 10, the situation is different. We need to count all pairs I, j, where the elements are equal and verify whether I asterisk j, %10 equals 0. This will result in multiple valid pairs, as we'll see next. For nums equals 1, 1, 1, 1, and k equals 10, we calculate all pairs I, j, that satisfy the conditions. For example, 0, 1 is valid because nums, 0, and nums, 1, are both 1, and 0 asterisk 1, %10 equals 0. Similarly, pairs like 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3 also satisfy the conditions. Counting all these pairs gives us a total of 6 valid pairs. Therefore, the output for this input is 6. This example highlights how arrays with repeated elements can produce a higher count of valid pairs, depending on the value of k. Finally, let's review some constraints and edge cases to keep in mind. The length of the array n is between 1 and 100, and each element in nums as well as k is between 1 and 100. For edge cases, if n equals 1, it's impossible to have valid pairs since I less than j cannot hold. If all elements in nums are distinct, the result is 0 because there are no equal elements to form pairs. If k is very large, certain values of I and j might always satisfy I asterisk j, %k equals 0, creating many valid pairs. Finally, when all elements in nums are the same, the total count depends entirely on the divisibility condition. Testing with extreme cases, such as a large array where all elements are the same and k is also large, helps ensure the solution is both efficient and correct. To tackle the problem of counting equal and divisible pairs in an array, we can start with a straightforward brute force approach. This involves using two nested loops to iterate through all possible pairs of indices I, j, in the array, where I is less than j. For each pair, we check two conditions. First, whether the elements at these indices are equal, meaning nums, I, equals nums, j, and second, whether the product of the indices, I asterisk j, is divisible by the given integer k. If both conditions are satisfied, we increment our count of valid pairs. While this method is intuitive and simple to implement, it operates with a time complexity of n squared, since the outer loop runs n times and the inner loop runs roughly n1 times on average. This quadratic time complexity makes it impractical for larger input sizes. However, the space complexity is O1, as we only use a single variable to keep track of the count, without requiring additional data structures. The brute force approach, while easy to implement, has significant trade-offs. On the positive side, it is straightforward and requires minimal effort to understand or code. However, it is highly inefficient for large arrays because of its quadratic time complexity, making it unsuitable for scenarios with higher constraints. To address this inefficiency, we can consider an optimized approach using a hash map. The core idea here is to group indices of identical elements together in a hash map, where the keys represent the unique values in the array and the values are lists of indices where these elements appear. Once we have these groups, we can focus on identifying valid pairs within each group, significantly reducing redundant comparisons. For each group of indices, we iterate through all possible pairs, I, j, and check if the product, I*j, is divisible by k. Constructing the hash map requires n time, and the process of generating and checking pairs depends on the size of the groups. While the worst-case complexity remains n squared, this is rare, as grouping eliminates many unnecessary comparisons. The space complexity for this approach is n, due to the storage required for the hash map. While the hash map approach reduces redundancy and is more efficient in many cases, it also comes with trade-offs. It is slightly more complex to implement and, in the worst case, still has quadratic time complexity. Ultimately, we chose the brute force approach as our primary strategy for its simplicity and clarity. This method is sufficient for smaller input sizes and avoids the additional space overhead associated with the hash map solution. The decision to use brute force is based on a balance of factors. The problem constraints often indicate whether optimization is essential, and for smaller constraints, the brute force approach is more practical. The hash map approach becomes advantageous when the array contains many repeated values, leading to large groups of indices. However, since the brute force method is easier to understand and implement as a baseline solution, it is a suitable choice for tackling a broad range of test cases, while the hash map method can be reserved for scenarios with higher constraints or more complex input patterns. To solve the problem of counting equal and divisible pairs in an array, we need to identify all pairs of indices, I, j, that meet two specific conditions. First, the values at these indices must be equal, meaning nums, I, equals nums, j. Second, the product of their indices, I*j, must be divisible by a given integer k. We begin by understanding the brute force approach. This involves using two nested loops to iterate over all possible pairs, I, j, where I is less than j. For each pair, we check both conditions, whether the elements at nums, I, and nums, j, are equal, and whether the product of their indices is divisible by k. If both checks pass, we increment a counter that keeps track of valid pairs. Finally, after evaluating all pairs, we return the counter as the result. While this brute force method is straightforward, it has a major drawback. Its time complexity is n squared, where n is the size of the array. For large arrays, such as those with tens or hundreds of thousands of elements, this approach becomes extremely inefficient. To address this inefficiency, we turn to an optimized approach that leverages a hash map. The idea is to store the indices of elements as we iterate through the array, which allows us to avoid the double iteration of nested loops. This reduces redundant computations and makes the algorithm more efficient. Let's break this optimized approach into steps. First, we initialize a hash map called frequency to store the indices of each unique value in nums. We also initialize a counter, count, to 0, which will track the number of valid pairs we find. Next, as we iterate through the array, for each index I and value nums, I, we check if the value already exists in the hash map. If it does, we retrieve the list of previously stored indices for that value. For each of these indices, we check whether the product of the current index I and the previous index j satisfies the divisibility condition, I*j, %k equals 0. If this condition is met, we increment the counter. After processing the existing indices, we then add the current index I to the hash map under the key nums, I. Once we've processed all elements in the array, we return the value of the counter as the result. This approach is not only more efficient but also avoids redundant computations by focusing only on relevant pairs. The use of a hash map ensures that we only check indices associated with values that match nums, I. This algorithm introduces several key insights. By using a hash map, we eliminate the need to repeatedly compare all pairs, significantly reducing the number of operations compared to the brute force method. The divisibility condition, I*j, %k == 0 is only evaluated for pairs that are relevant, further optimizing performance. The hash map provides average O(1) time complexity for lookups and updates, making the overall complexity of this approach n*m, where n is the size of the array and m is the average number of indices stored per unique value in nums. Additionally, the algorithm handles edge cases gracefully. For example, if the array is empty, it immediately returns 0. If no pairs satisfy the conditions, the counter remains 0, which is returned as the result. The algorithm also scales well for cases where all elements are identical, as the hash map efficiently tracks indices and checks divisibility without unnecessary computations. The space complexity of the optimized solution is O(n), as the hash map stores indices for all unique values in the array. To summarize, the algorithm initializes a hash map and a counter, iterates through the input array, and checks each pair of indices for the given conditions. Once processing is complete, it returns the total count of valid pairs. The pseudocode captures these steps clearly. It defines a function count_pairs that initializes the hash map and counter. As the array is traversed, it retrieves indices for matching values from the hash map, checks for divisibility, and increments the counter accordingly. The current index is then added to the hash map. Finally, the counter is returned. This optimized algorithm is both efficient and scalable, making it well-suited for large input sizes. This implementation solves LeetCode problem number 2176 by iterating through all pairs, I, j, in the input array nums and checking if they satisfy the given conditions. The method countPairs starts by initializing a variable count to 0, which keeps track of the number of valid pairs. It also calculates the length of the array, n, to use in the iteration. The outer loop iterates over index I from 0 to n1. For each I, the inner loop iterates over index j from I+1 to n1, ensuring that each pair is considered only once and that I<j is maintained. Within the nested loop, the code checks two conditions for each pair, I, j, whether the elements at these indices are equal, nums, I, == nums, j, and whether the product of their indices, I*j, is divisible by k, I*j, %k == 0. If both conditions are satisfied, count is increment. After examining all pairs, the function returns the final count, which represents the total number of valid pairs in the array. This algorithm has a time complexity of O(n²) due to the nested loops, making it suitable for moderate input sizes. This is the Java implementation of the LeetCode problem count equal and divisible pairs in an array. The logic mirrors the Python implementation. Key differences include the use of explicit type declarations for variables, standard Java class structure, and the absence of Python-specific constructs. The solution uses nested loops to iterate through all pairs, I, j, where I<j, checking both the equality condition for the elements and the divisibility condition for the product of indices. The time complexity remains O(n²), where n is the length of the input array. To solve this problem, we need to identify pairs of indices, I, j, in the array nums that satisfy two conditions. First, the elements at these indices, nums, I, and nums, j, must be equal. Second, the product of the indices I*j must be divisible by k. We start by initializing a count variable to 0, which will track the number of valid pairs we find. The length of the array, n, is also calculated so we can iterate through all possible pairs efficiently. Using a nested loop, the outer loop iterates over each index I from the beginning to the second to last element. For each I, the inner loop checks all subsequent indices j where j greater than I. This ensures we only consider each pair of indices once. Within the inner loop, we check the two conditions, whether nums, I, equals nums, j, and whether the product, I*j, is divisible by k. If both conditions are met, we increment the count variable, adding 1 to our total number of valid pairs. Let's walk through the first example to see the algorithm in action. The input array is nums equals 3, 1, 2, 2, 2, 1, 3, and k equals 2. Starting with I equals 0, we compare nums 0 equals 3 with all elements where j greater than 0. At j equals 6, nums 6 is also 3, so the first condition, nums I equals nums j, is satisfied. The product of the indices 0 asterisk 6 is 0, which is divisible by 2, satisfying the second condition. This gives us a valid pair, so we increment count to 1. Next, for I equals 1, nums 1 is 1, and we compare it with nums 5, which is also 1. The product, 1 by 5, equals 5, and since 5% 2 equals 0, this is another valid pair, increasing count to 2. For I equals 2, we compare nums 2 equals 2 with nums 3 and nums 4. Both comparisons satisfy the conditions, resulting in 2 more valid pairs and bringing the count to 4. Finally, we continue checking all remaining indices, but no additional valid pairs are found. The final count for example 1 is 4. In the second example, we use the input nums equals 1, 2, 3, 4, and k equals 1. The initialization is the same, count is set to 0, and we iterate through the indices using nested loops. With k equals 1, the second condition, I asterisk j, %k equals 0, is always true since any number modulo 1 is 0. However, we also need nums I to equal nums j, and in this array, all elements are distinct. For I equals 0, we compare nums 0 equals 1 with all elements where j greater than 0, but no pairs satisfy the equality condition. Similarly, for I equals 1, nums 1 equals 2 does not match any elements at j greater than 1. The same is true for I equals 2 and I equals 3, where no valid pairs are found. As a result, the count remains 0, and the final output for this example is 0. In the third example, we examine the case where nums equals 4, 4, 4, and k equals 3. Once again, we initialize count to 0 and loop through all indices using the nested structure. For I equals 0, nums 0 equals 4, and we compare it with all elements where j greater than 0. At j equals 1, nums 1 is also 4, satisfying the equality condition. The product, 0 asterisk 1, is 0, and since 0% 3 equals 0, we have a valid pair, so we increment count to 1. Next, for j equals 2, nums 2 is again 4, and the product, 0 asterisk 2, is also divisible by 3. This gives another valid pair, increasing count to 2. For I equals 1, we compare nums 1 with nums 2. While the elements are equal, the product, 1 by 2, equals 2, which is not divisible by 3, so this pair is not valid. No further comparisons are needed, and the final count for this example is 2. To analyze the time complexity of the solution, we start by breaking down the nested loop structure. The outer loop iterates from I equals 0 to I equals n1, giving us n iterations in total. Inside this outer loop, there is an inner loop that begins at j equals I plus 1 and runs until j equals n1. This means the number of iterations for the inner loop decreases as I increases. For example, when I equals 0, the inner loop executes n1 iterations, but when I equals 1, the inner loop executes n2 iterations, and so on, until the last iteration where I equals n2 and the inner loop runs only one time. Summing up all these iterations gives us the total number of inner loop executions, which can be expressed as the sum of the first n1 natural numbers. Using the formula for the sum of an arithmetic series, this total is equal to n asterisk n1/2. This summation is the dominant contributor to the time complexity. Now, within the inner loop, the algorithm performs two constant time operations for each pair, I, j. The first is a comparison to check if nums, I, is equal to nums, j, and the second is a modulus operation to verify if, I asterisk j, %k equals 0. Since both of these checks take O1 time, the cost of pair verification is directly proportional to the total number of pairs. As calculated earlier, the total number of pairs is n asterisk n1/2, which simplifies to O n squared. Therefore, the overall time complexity of the algorithm is O n squared, dominated by the nested loop structure. For space complexity, the algorithm only uses a handful of variables such as count, I, and j in addition to the input array nums. These variables require constant space, meaning the auxiliary space usage is O(1). Since no additional data structures are used, the overall space complexity of the algorithm is O(1). When we analyze the best, average, and worst cases, we see that the time complexity remains O(n)² across all scenarios, as the total number of pairs checked does not change. In the best case, pairs may fail the conditions early, but the nested loops still iterate through all possible pairs. In the average case, assuming a random distribution of values in nums, the number of iterations remains the same. Even in the worst case, where many pairs satisfy the conditions and all checks are performed, the number of iterations again stays constant. Comparing this approach to potential optimizations, we see that it represents a brute force technique, explicitly checking all valid pairs, I, j, or I less than j. While the O(n)² complexity is inherent to this method, optimizations could involve using a hash map or frequency array to group indices of equal values, reducing redundant comparisons. To summarize, the algorithm has a time complexity of O(n)² due to the nested loops and pair checks, a space complexity of O(1) because it uses constant auxiliary space, and identical time complexity across best, average, and worst cases. Although this brute force approach is straightforward, exploring optimizations could yield performance improvements in certain scenarios. When tackling this problem, there are several common mistakes to watch out for. First, not checking edge cases is a major issue. For example, if you're given an array with only one or two elements, or if all elements are identical, failing to account for these scenarios can lead to runtime errors or incorrect outputs. It's important to remember that edge cases are often used in testing or interviews to evaluate your solution's robustness. Next, be cautious with how you handle the modulo operation. Some mistakenly check only if j equals 0, without considering that in certain variations of the problem, you might also need to check if j equals 0. Missing this detail can result in overlooking valid pairs. Another pitfall is relying on brute force solutions for large inputs. With an O(n)² approach, if the input size is greater than 10,000, you'll likely run into time limit exceeded errors. This is why scalability and optimization are critical. Lastly, don't overlook problem constraints, such as assuming all numbers are distinct or ignoring whether they are non-negative. Misinterpreting these constraints can lead to flawed logic or unnecessary complexity in your solution. Additionally, modifying the input array during your solution is another common error. For instance, sorting the array in place without confirming whether the problem allows modifications can cause side effects that affect other parts of the program. This is particularly important when the input array might be reused elsewhere. As for interviews, there are some key insights to keep in mind. Problems involving pairs or triplets, like this one, often benefit from recognizing patterns. Hashing techniques or leveraging mathematical properties can provide significant optimizations. Interviewers may also assess your ability to balance brute force and optimized approaches. It's a good idea to start with a simple, clear solution and then discuss how you could improve it. Finally, always articulate your thought process clearly. Explaining why you chose a specific approach helps interviewers understand your reasoning and problem-solving skills. Now, let's explore some related problems and alternative approaches that can help deepen your understanding. Similar problems include LeetCode 1512, which involves counting good pairs, and LeetCode 1395, where the task is to count the number of teams that satisfy certain conditions. Other examples include LeetCode 2006, which focuses on pairs with a given absolute difference, and LeetCode 217, which deals with identifying duplicates in an array. As for solving this problem, the brute force approach is the simplest alternative. It involves using two nested loops to iterate over all pairs, I, j, and checking the divisibility condition. While this method is straightforward, its time complexity is O(n)², making it impractical for large inputs. A more efficient alternative is to optimize using a hash map. By storing the frequency of elements, you can check divisors for each value using divisibility properties. This method usually achieves O(n) complexity, assuming divisor computation is efficient. However, it does require additional space for the hash map, so that trade-off should be considered. Another approach to consider is sorting the array and using the two-pointer technique. This method involves sorting the input array first, which has a time complexity of O(n log n), and then using two pointers to identify pairs that meet the divisibility condition. While this approach is more efficient than brute force, it comes with certain trade-offs. For example, sorting modifies the input array, which might not be allowed in all variations of the problem. Additionally, it may not work for scenarios where the order of elements or the original structure of the input needs to be preserved. Choosing the right approach depends on the specific constraints and requirements of the problem, so always evaluate the trade-offs carefully before deciding on your solution strategy. Great work! In summary, we analyzed the problem, explored an initial brute force solution, and discussed improvements. Remember to focus on efficiency and trade-offs when solving similar problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!